Welcome to today's CyLab seminar. And before we get started, I just wanted to remind you, we encourage questions. If you have any questions, please hold down the microphone button so that our partners who are viewing the seminar can hear your questions. So today we have Michael Farb, who is presenting SafeSlinger, an easy-to-use and secure public key exchange. And you can download SafeSlinger on the iPhone or Android markets. I've done that myself. Michael joined CMU as a CyLab research programmer in 2010 after years of experience in digital publishing and mobile software development at Nuvo Media and FedEx Ground. At CyLab, he is working with researchers to provide smartphone users with practical solutions for securely exchanging identity data. So welcome, Mike.
Thanks. Let me just make sure this is, everyone can hear me? Okay. Thanks, Michael. Is this okay? Everyone in the back? It's good? Okay. So welcome, everyone. I get the privilege of sharing this project with you. We have a big announcement to make. The SafeSlinger is now open source. I'll give you some information about how to use it and where you can find it later on. But as a way of introduction, I'm an engineer. That's my background and experience, and I'm lucky enough to work with other researchers, Yushin Lin, Tiffany Hyunjun Kim, Jonathan McCune, and Adrian Perig on this project. And what we're really talking about is we have this setting of we want to exchange information to secure communications. We might exchange a cryptographic key to do that. We want to leverage this digital exchange of information. We want to prevent sharing that digital information in such a way that someone can alter it. We want to ensure authenticity of that cryptographic key. So we might leverage a physical interaction, like a meeting or a phone call, to pair an actual physical meeting where you can assure yourself of the person you're communicating with and an actual digital exchange. And we want to do this in a way that's easy for people to use, where there's no current commonly trusted infrastructure, an open infrastructure. A couple of prior ways of doing this, like I said, a public key infrastructure, we may not want to use that because we want to do this ad hoc. We may not have the money to establish a PKI. PGP is a pretty good way of communicating securely. It does take a little bit of sophisticated use. There is a little bit of ramp up to learning to use it. We want to see if we can provide something that's easier. So one way we might share a shared secret is by two parties sharing a shared secret for further use with the Group-Diffie-Hellman Protocol. So the way that works in general is A will share some public values with B. B will do the same in the opposite direction. And then those two values can be computed to determine the same equivalent shared secret, which they can then use to encrypt communications. So the problem is the man-in-the-middle attack. We have an attacker who has the ability to intercept and alter any of our communications. If we're on a wireless channel or even any kind of in-band channel. Wireless is invisible, and so while we broadcast a public value, we think to B, it could be intercepted by M. M could then generate its own value to share with B, and vice versa. And so what we get is, instead of A communicating to B, A and B communicating only through M, which is not great. This is not secret. The way we can get around this is checking the integrity of the shared secret to detect the man-in-the-middle attack. Are they serious? Since wireless communications is invisible, people can't tell which devices are connected. We're all of our bits are floating around in the air. A neighbor can easily execute a man-in-the-middle attack. We can't see them. We don't know what they're doing. It's easy to perform, and we need an out-of-band channel to verify this physical interaction. So we have our in-band channel where we're trying to communicate this key. We're trying to share it over a wireless medium. We have an active attacker who can intercept. If we use an out-of-band channel, a cable, NFC, maybe Bluetooth, human visual channel, if we pair those two, we have a chance of catching any interference by the attacker. Of course, there are quite a few different ways of doing pairwise out-of-band channels. Password entry using Bluetooth simple pairing, string comparisons, audio comparisons, graphics, shaking the devices, detecting the vibrations between them, NFC. So you might think that's all great, but there are still issues. Our goal is to provide a nice way for people to exchange public keys in a group setting. So this is a little inconvenient since most of these connections are pairwise, doesn't scale. N number of members have to perform order of n squared interactions. For a group of 10, that's 45 separate interactions. Another attack we want to guard against is a group in the middle attack, which is kind of interesting. In this case, all members share a secret, and all members know the number of members present. The attacker can separate the intended group into multiple groups. And so if our attacker is Red Pac-Man, and he's malicious, he can separate those those other three users. The victim members believe they are part of a group of 4 members with 3 others, but instead they are a separate group with the adversary and some fake identities. There are other ghosts there representing who we think the actual intended people are. So the goal for us, definitely authentic group exchange of information. We want 5 properties in our exchange. We want scalability, we've discussed a little bit. We want authenticity, we want to make sure each user should obtain the correct contact information. We want secrecy. Whatever medium we're doing this over, we don't want to leak any potentially sensitive information. We want usability, we want a nice, easy-to-use interaction with as few steps as possible. And we want portability. We want to leverage, say, the device that we all carry around. If it's a cell phone, smartphones are more and more available, and with that computing power, we want to make sure that the most available platforms are in use, like iPhones, like Androids. So one of our challenges was, if we're going to do this and communicate between Android and iPhone devices, and we want an out-of-band channel or even an in-band channel to communicate, since we're leveraging a meeting, we might do that locally, physically. So a technology we might use is Bluetooth, NFC, Wi-Fi. But we have some challenges there. NFC is slowly becoming available. I don't even think it's available yet on iPhones, maybe on the iPhone 6. Does anyone know? No. Bluetooth, there are some integration issues with iPhones. Only iPhones and iPhones can communicate over Bluetooth, although that's changing. There's low energy Bluetooth, which is another protocol, but that's still to be widely adopted. So to sidestep that, we use a server to exchange our messages. We just have to make sure that everything we're doing doesn't leak any information, in that though we're using a server to exchange, we want to make sure if the server is malicious, there's no loss of authenticity or leaking of information. So what this comes down to is our protocol. This is a few lines from the paper that was published at MobiCom this past fall. There's a lot of steps here. The main intuitions I would leave you with are, we have a setup of a commitment tree, and I'll explain that in a little bit. But we have various levels of authenticity checking for anyone in the group before we actually construct a shared secret before we use a Diffie-Hellman protocol. So we want to make this simple. If we have 3 devices, we give the users the opportunity to modify the data they may want to share with each other, let them start, and then a few bits of information. One is obvious, the number of users, but we use that to protect against receiving too many bits of information from sources like an attacker. Now we have our first of 2 out-of-band comparisons that we require our users to do. One is, this is a grouping scheme. And what we're trying to do is, we're not leaking accelerometer data or geolocation data to determine that you're in the same location. So if we're all communicating to the same central server, we want at least some assistance to group together. Time is definitely a factor, but several groups doing it at the same time can get a little muddy. So what we do is we allow the server a little bit of logic to assign us a very low entropy ID, and then each user enters the lowest common ID of each member in the group, and that's how we achieve a little bit of grouping. The second comparison is the users are given a hash of their data, which is represented as a 3-word phrase. And they have to determine where on any of these screens the same phrases, so they have to compare that out of band. They have a little bit of work to do there. And at the end, we get some results. This is our decrypted data that we've shared. This is a simple representation. Our actual implementation is using a complex vCard with some public key data and other data. So we want that to be easy to use. We only have 2 out-of-band comparisons. Some of our challenges I spoke about earlier is we want to make sure we aren't leaking any information. So the server can learn the contact information of all users if we are not encrypting the data that we're sharing. So our approach is to use the SCR protocol, which is a Group-Diffie-Hellman exchange. And we use that to create a shared key under which all information is encrypted. And then only at the end of our protocol, when all the verifications succeed, then we release the decryption key. So what this looks like a little bit is, if I have users X, Y, and Z, and Diffie-Hellman is a pairwise exchange, then X and Y can create some public values, share them to produce a shared secret, GXY, but that's not very useful to Z. So what they can do then is take their node, the public form of that node, and share it with Z. And once Z has that, then all members can now construct the master key K. Second challenge is this is more of a user interaction. We want to prevent automatic dialogue failure. We want to prevent people from just clicking next or OK, just let me through the next dialogue. I want to do the exchange. So we could present them with one hash that they need to read out of band. We can't guarantee that they will do the comparison. So what do? We give them 2 decoys. And we don't have any default choice. It's in random order. So each user has to decide. They are forced to communicate out of band to determine which of these 3-word phrases matches on any and all phones. Our third challenge is we want to make sure that we're not revealing information on protocol failure. When the protocol fails, we don't want to leak, right? No information. It's an all or nothing property. We want all members of the exchange to share that they found a match out of band with all other members. So to do that, our approach is to create a commitment tree with several commitment stages. So our commitment tree looks like this at the beginning when we're beginning constructed. I'll go through the creation phase and show you how the commitment tree is constructed, and then I'll explain how those pieces of information are exchanged. Okay. So we start off with two nonces, two random numbers. One nonce M, which is the positive answer at the end of my exchange. Yes, I found a match. One represents I found an error, or I found no match. And I have a Diffie-Hellman public key that I'm going to use later. I construct that now as well. And I also take my data. In this case, we're using a complex V card as our data. And I use that nonce. This is the information up here I'm going to reveal last. And I use it to encrypt my data. So we perform a couple of hashes at this stage to later determine which answer the users are giving. And we give one extra hash to the correct answer because we want to make sure that we don't reveal it too soon. I perform a few more hashes to take all this data into one master commitment. A commitment is the first piece of information that any users will exchange with each other. And once they have that, they can now begin to disclose the next level of information in the tree. Now what they'll do at this point is now we have an opportunity to authenticate that the data that we have received belongs to the people we intended. So we can now take those values, those three triad of values, for any members of the current exchange, hash them together, and come up with a three-word phrase, which is a 24 bits represented with the PGP word list of the initial form of the hash. So now my users have some choices. I can, of course, say that I didn't find the match out of band. That could be because of some network interference, either intended or not intended by an attacker, right? And to do that, I share two sets of values. The hash on the left, and then my error nonce. So when I share that with all other members of the exchange, I can take a look, see if I can create the hash here, take these two values, and it better equal this. Only if I think it's the error case. If not, the other case is I will do the opposite, really take these two values, hash it, and if that's my answer, then that user delivered the match case. So at this stage, I can now, I've validated that I wait for all users to give me their answer. If all users attest that I found a match out of band, then we can construct our Diffie-Hellman shared secret and encrypt this private key and share it. So our last challenge in this set of challenges is the group in the middle attack, where a malicious group member will perform. We have the users enter the number of participants to ensure that on the client level, we're getting all the data that we expect. All users need to compare the word list, and it makes the group in the middle attack more of a daring attack with a success probability of 2 to the negative 24, based on the number of bits we're using in the out of band. So we couldn't find any product that allowed a group exchange, a secure group exchange of information, like sharing a public key or even sharing contact data. But Bump is certainly one of the more popular ones. We did some comparisons with Bump, and it provides not group exchange, but pairwise exchange of information. And we did an evaluation, and sort of on the outset to compare them, Bump doesn't provide the scalability that we do in SafeSlinger. The exchange mechanism has to be physical for Bump. You have to bump your phones together, and then you release your accelerometer data and geolocation data to their server, which it then does the grouping for you. In our case, we don't have to be in the same room. We can be on a video chat, we can be on a phone call, and just as easily share the grouping ID, the lowest number ID, out-of-band comparison, just as easily share those three words. So we want to measure the efficiency of this, so we had a small user study. We separated into groups of 2 people, 4 people, and 8, had them randomly assigned to those groups, and we asked them to, we showed them how to use Bump, we showed them how to use SafeSlinger, and we asked them to exchange their contact data using both protocols. So the results were interesting. When you look in the case of 2 people trying to exchange their contact data, it's actually a little bit faster with Bump. And one of the reasons is Bump is releasing more information, leaking more of your device's information onto the internet and into their servers to compare you, to find out which set of users are trying to exchange data at the same time. In our case, we have a little bit more internet interactivity, a few more server calls. So that adds a little bit more time for us. But once you start to get the goal of trying to do a group exchange, it's a little more difficult because now I have 4 people in the same room who are all trying to Bump at the same time. And it gets a little messy. It's only really somewhat clean if everyone waits for order of n squared interactions. Right? And it gets really, really nasty up here. So what can we do with this now that we have a secure way of exchanging our private keys? What we have in Michael mentioned on the App Store and in Google Play is a secure text messaging app which leverages this exchange. So it provides some features you might expect a text messaging app to provide. And we also have this interesting property that we can use both the text messaging app and the secure exchange to leverage one-hop extension of trust. So the way this works is if I have had a direct exchange, a SafeSlinger exchange with some other user, or some other sets of users that, say, a third person hadn't been able to do in person, I can then introduce those two, White Rabbit and Cheshire Cat, and send the public key encrypted in our text messaging app to those 2 users, which they can then receive and import. And so in my contact list, I can see a list of the people that I've had direct exchange with, and I can see the list of people that, alongside that I've had one-hop extension of trust, what we call secure introduction. And so where are we going to go with this? Let me stop for a second and see if anyone has any questions for me at this point. That was a lot of information. Okay, okay. So we have our project now as open source. You can find it on GitHub. All of our server code, all of our iPhone code, the messaging app, and the exchange that we use. Same for Android. And what we've done was we tried to move the code into a nicely usable exchange library, as well as a demo, and you can also see how the messenger application, text messenger application uses the library. It doesn't require much to use. I'll give you a quick example of that. And that's ongoing. The Android form of that library, nicely separated out for you, is ready to go. and we're still working on separating the iPhone code. The next sort of features that we want to introduce are some email integration, some different ways of doing the exchange over a local protocol. While a lot of our phones are able to access the internet and are accessible to most servers, there are places in the world where people don't have that luxury, and there's some filtering going on. They cannot contact our server. So we want to, not only for convenience sake, but also for users that don't have that ability, to perform a local exchange of their keys. We're considering NFC and Bluetooth at the moment. I'll get into some of the challenges with that. And then our future work is, we want to see if we can expand this to more platforms. We've had some user requests for Windows Phone. That's certainly a probable target. And we also want to see if we can extend this method of exchanging trust, this ad hoc method of exchanging trust, to something more established. So can I use my smartphone to establish trust with a kiosk or an ATM, something, some sort of smart machine at a conference, say? So this is just a screenshot of our GitHub project. We separated the repositories. App Engine is what we run our server on. One of the things I'm curious about are what other sort of server solutions people are interested in. Do you want a PHP server with MySQL? These are some options. Our Android and iPhone complete source, and we have there we go. No. We have also a repository if you're just interested in helping localize some of the language strings in the application. You can find those there. So what we have now separated, at least on Android, is an App Engine server that you can download. You can go into App Engine, create an app, plug in our server. You'll have to change the name because I think there will be a name conflict with one that we've already deployed. And then use our Android library and demo. What you see here is just a screenshot. This is most of the code of the demo. It just calls the Exchange library. And it really requires very little. It's probably 50 lines of code, just the demo. And it just requires a location of where your server is and the information that you want to exchange. This, of course, is a UI view. You probably want some other better integration under the covers if you use it. Like I said, the iPhone version of this is coming, and the documentation is not great on GitHub, admittedly. We need to provide a really good set of instructions for developers who want to use this. So that's forthcoming. So can I do this local exchange over NFC and Bluetooth? We have some opportunities and challenges. It definitely could be interesting to do this. Like I said, NFC is being slowly added to Android, even slower on the iPhone. Bluetooth is restricted on some platforms of iPhones. NFC might hold some promise of letting us sling keys as a supplementary method of doing this. If we provide the internet exchange as the primary method, we might have an opportunity to take two NFC-enabled devices and bring them together. Those devices can announce their public key to each other. If we find that their public key ID, if we find that they aren't in our current library, we could bring up some notification, which asks them, Alice is ready to validate your key. Are you ready to do the same? Right? If that's true, of these elements, this protocol and these sort of three screens that we bring up when we do the exchange, we can eliminate some of them. if we're using NFC, we know we have 2 users. We don't need to select from a list. We can avoid the grouping because we know the channel we're on is our only group. And then there's massaging of the protocol. Some parts can be removed, and perhaps there are more. So this is something we're thinking about. We want to do this in a way that is useful but not confusing to the user. If I give someone a screen that says, do you want to connect on internet, or do you want to connect on Bluetooth or NFC, it can be a little messy. So how can we have you guys join us in this project? Please rate us on any of the app stores. You don't have to give 5 stars. That's a suggestion. You can audit our code, review it, find bugs. Would be really great. If you're interested in translating any of the languages, or just experiment. If you have a student project that you're interested in doing, please fork us on GitHub and let us know what you're doing, and we'll help you if we can. So this slide I added last night because I realized since we've been doing this, we've had a lot of people helping us design, implement this, a lot of analysis. There have been other student projects that have been analyzing the protocol, tons of translation help, and so this is a way that we can show you the number of people that have been involved in this. I do give Adrian a little more credit for the testing because he tried the hardest than most to break the thing. So I'll give him some good credit for that. And then down here, I also pointed out Yan Yim created a nice little animation for us to sort of on a high level explain to users that are wondering what the value of a secure identity exchange is on our website. And I have a shortened version of it. This one is actually, I think the one on the website is 3 minutes. I think this is just 1.5 minutes. But to show you an idea of what
in our digital world, where attackers exist. After a meeting, people want to send messages over the internet. However, not many people know that attackers can observe and alter their messages. Moreover, the stolen personal data can cause serious problems, such as spam or phishing attacks. What can we do to protect each person's identity data? We can use cryptographic keys to render the message useless to attackers. We cannot secure the entire internet, but we can secure a small section of it. We've developed SafeSlinger to do just that. SafeSlinger generates secret keys when people meet. That data is combined on each phone, and validation information is displayed as a 3-word phrase. When each person selects the same set of words on each phone, the identity data is revealed. This also works the same way in larger numbers of people. It's like handing a friend your business card, printed in invisible ink, and only your friends can read it. Whether meeting in person or over the telephone, you have the assurance that the other person is real. SafeSlinger is available for Android devices, as well as iPhones, iPads, and the iPod Touch. We can compose a text message or add an attachment and select one of our secure identities. SafeSlinger will sign the message, encrypt it, and send it through the internet. When our message arrives, it can be decrypted and verified with the keys we exchange. Now, people can send messages to each other securely. You can be sure that messages are sent only from the same people that you shared identities with, and that no one else can read your messages.
So that's just an overview that we put on the website and the Google Play Store to people who are wondering what this thing is, what it does. But believe me, if you get a chance to do something like this in your project, this is the most fun meeting you'll ever have. In summary, we've tried to design this group solution to exchanging identity data from anywhere from 2 to 10 people in a way that maintains user privacy, that only group members can learn to exchange information, and we're not leaking any of that information. We want it simple to use, resilient to user error. We want rich applications that can be built on top of it, secure messaging or introduction or other things that you may come up with. And there's a web page link there. There's a lot of information there. Our paper, links to the GitHub site. Various presentations are also available there. And you can use my email is mwfarb at CMU, or our support app if you have questions. But thanks very much. So does anyone have any questions?
So what all is actually stored on the server? You said like it doesn't learn information. Like, do you store it? What do you store?
What's stored on the server? The commitment tree that I walked you through with those green and red and blue boxes. So each of those sets of information are posted on the server. And we construct it in such a way that the information itself isn't useful unless I can do my out-of-band comparison, and I have users which can attest to the authenticity of the information. So, yeah. Okay. So let me know if you have any questions, or if you want to use the project, and if you have ideas, let me know. Love to talk about them.